Hello, everybody. It is a great day, and I wanted to say good morning, good afternoon, and good evening to all of those that are here for our forensic webinar on the high resolution imaging. So, first, what I'd like to do is just do a brief introduction to myself as well as the platform that you guys are looking at while we allow for some attendees to join. My name is Rachel Lieberman, and I am the current marketing manager, global market manager for Waters for the toxicology and forensic division here as a part of our CBU. And I have my colleague Nayan here, who I will introduce shortly. He will be the man of the hour. So first, what I would like to do is give a brief housekeeping update for the particular slides that you will be seeing. So one of the things that we'd like to have is some attendee interaction during the presentation. So please use the Q&A box to ask any questions throughout the webinar. We will be monitoring the Q&A session as we go through, and then we will answer them at the conclusion of the presentation, in which we will have a conversation with Nayan to go over these questions. Additionally, in the center, you will see the slides that are used for the presentation and the video. And then below the slides, you will see a resource list with any kind of additional information and applications related to this topic. On the right-hand side, you will find the speaker bio as well as a survey. This survey is really important for us as it helps us to find out more information about our webinars, make sure that they are useful, as well as any kind of new materials or things that you would like to see from us in the future. We really do take in that feedback. And so feel free to fill that out anytime during the presentation. And we will be able to review that for later times. If at any point you are unable to see these windows, the icons at the bottom of the page are there for you to expand them if you're unable to see them. So next, I would like to introduce our today's speaker. So Nayan Mistry is a senior application scientist at Waters Corporation. He joined Waters in 2009 and has been a part of our global team dedicated to performing research and development of applications and analytical solutions for forensic toxicology. His key focus is on toxicology screening, and he has expertise in both the nominal mass and accurate mass-based screening solutions using Unify and Waters Connect application software. He plays a key role in the development of these solutions and in the expansion of associated libraries. He is currently playing a key role in the development and support of the recently launched Xevo G3 QTOF mass spec and the MRT that we will be discussing today, in addition to other responsibilities in the nominal mass applications. His favorite aspect of the role is customer support, and he's greatly involved in global on-site customer support and training, and has presented his work at various conferences worldwide. So I'm happy to introduce Nayan today, and I will turn it over to him.
Brilliant. Thank you very much, Rachel. Good morning, good afternoon, and good evening. Everyone, thank you very much for attending this webinar. Hopefully it should be informative for you guys, and I look forward to your questions at the end of this session. So the presentation will cover the basics of accurate mass before discussing the Waters high resolution screening solution that we currently have, and also discuss some things of what we have coming up. So why use screening for toxicology? We want to know what is actually in the sample. There are several targeted techniques used in toxicology laboratories for drug detection, and these include immunoassay and LC-MS type analyses. However, more and more laboratories are wanting to understand what else is actually in the sample itself. This is where the non-targeted or discovery type of analyses come into effect, playing a vital role in helping to look for new emerging drugs. Over the last 10 years, there have been an increase in novel psychoactive substances, or NPS, often referred to as legal highs, designer drugs, and bath salts. These drugs mimic the effect of traditional narcotics such as heroin, cocaine, and cannabis. And a particular problem in the US today is the actual use of synthetic fentanyls. Fentanyl is a drug used in pain management since the 1970s. Illegally produced drugs that are similar to fentanyl are available, and because of their potency, they're playing a role in hundreds of deaths in the States. So this slide is just highlighting some of the problems faced with novel psychoactive substances. New analogs are constantly emerging, including fentanyl analogs and the nitazenes in recent times. With the new substances coming onto the market, it's difficult for the standards agency to keep up with the manufacturing of them. It's in these situations where the high resolution mass spectrometry shines. Tandem quadrupoles in MRM mode would miss anything they were not monitoring, and immunoassays are not always available for new compounds. So let's take a quick look at the fundamentals of high resolution mass spectrometry. I promise I won't take too much of your time on this section. As you may have noticed, high resolution mass spectrometry has seen a steady rise in popularity over the last 20 years to be a powerful technique in various scientific disciplines. It's in forensic toxicology, however, when this technology significantly benefits the scientists. High-resolution mass spectrometry brings a number of advantages, the main one being specificity in identification. This is owing to the ability to provide mass values to 4 decimal places. This in turn increases confidence in identification and reduces false positive detections. There are 2 terms highlighted here which are used in high-resolution mass spectrometry, and these are exact mass and accurate mass. Exact mass is the mass calculated based on the formula itself, and the accurate mass is based on the measured mass. So here we have an example of 3 compounds. All 3 of them have different elemental formulae, yet the nominal masses as a protonated species are the same, mass to charge of 278. Therefore, a nominal mass instrument would not be able to distinguish between them based on precursor mass only. However, when we look at the exact masses as a protonated species, they are quite different and therefore can be easily differentiated using high-resolution mass spectrometry techniques. The basic principles of time of flight is how long it takes for an ion to travel from point A to point B based on its mass or size. So here's a schematic of what happens in the flight tube. The ions will have the same amount of kinetic energy. However, the lighter molecule will move faster, so we'll have a shorter flight time. So in summary of that first section, the benefits of exact mass instrumentation means a mass can be measured up to 4 decimal places compared to 1 decimal place using a nominal mass instrument. Exact mass is currently used in a range of application areas such as environmental analysis and clinical screening for drugs of abuse, where rapid confirmation and low detection with high level of confidence are required. The specific data acquired using TOF technology gives a high level of confidence when confirming target compounds. In the case of unknowns, it is possible to predict an elemental composition with confidence. The following slides will we will take a look at the toxicology screening solution itself. The solution configuration comprises of the LC and the G3 QTOF, the Waters Connect informatics package, which encompasses the toxicology library as well. Data is acquired in full-scan MSE mode. So what is MSE? It is a data-independent acquisition mode, which involves a rapid alternation between 2 energy levels. The low energy provides the accurate mass of the intact precursor ion, and the elevated level, 10 to 40 electron volts, provides the accurate mass of the fragment ions, and all done in a single acquisition, followed by time alignment of the data so the fragment corresponds to the correct precursor ion. So why is it important? Supporting information such as fragment ion information helps to reduce the number of false positive identifications during screening analyses. So what are the benefits? Well, it's simple to use and set up and requires no method development. It generates all data in full scan, so you have all the data all of the time, and retrospective analysis is possible, unlike MRM type of analyses. The schematic above shown gives a visual representation of how MSE works. So screening experiments are entirely dependent on the quality of the library and not the quantity. The more information you have, the more specific the results. The three essential elements that constitute to a good quality library are the presence of the precursor mass and associated retention time and fragment ion information. As the library has evolved, we have tried to keep its content current and in line with the latest drug trends. The current version of the library has in excess of 2,000 compounds, with approximately 85% of these entries having at least one diagnostic fragment ion, which have been verified by collaborator sites, and over 98% of these entries have mole files or chemical structures to assist with semi-targeted analyses. So this is just an example of a library entry showing a fentanyl analog with its precursor ion and fragment ion highlighted, as well as the retention time. And this slide summarizes some of the main drug classes we have included in the toxicology library. The following slides discuss the method and the data processing in a little more detail. The screening solution, as I mentioned before, is supplied with the application media, which consists of two methods, a positive and negative analyses method. Shown here is a positive method, which includes a 15-minute chromatographic separation and the mobile phases A and B. Here's a shorter negative method at 7.5 minutes. Notice how the column and the acquisition range and MSE method are the same for both methods, and it's only the mobile phases and chromatographic gradient that are different. The data can be processed in three ways: a targeted analysis, a semi-targeted analysis, and a non-targeted or discovery type of analysis. During the targeted analysis, data is simply matched to a library, the criteria for which is shown in the blue box here. And that's for a positive identification. So here's an example of a cough medicine following a 100-fold dilution with all 6 target analytes successfully identified using the positive identification criteria, all with good mass accuracy of less than 2 parts per million for the precursor, and all expected fragment ions found. The constant threat of novel psychoactive substances emerging onto the drug scene has always posed a major analytical challenge, as not all substances are well characterized or commercially available, and therefore keeping the library current can be an issue. As MSE data is collected in full scan, semi-targeted analysis is possible. The Waters Connect informatics package allows for the use of chemical structures or mole files to assist in providing probable identification based on precursor mass and supporting fragment ion information. The toxicology library contains several entries that don't have diagnostic fragment ions, but they do include the mole files. The software will match the high energy MSE spectral data to the theoretical fragment ion information, which are generated as a result of the in silico fragmentation. The fragmentation process is performed automatically as part of the data processing step, so reprocessing is not required. If a match is successful, a structure is assigned to the measured high and low energy spectra. The in silico fragmentation process is also performed for entries that do have verified diagnostic fragments, providing extra confidence in identification, in addition to providing supplementary fragment ion information also. A major highlight for high-resolution mass spectrometry instrumentation is the ability to perform non-targeted or discovery type of analyses. Structural elucidation is a powerful feature of Waters Connect, and it's an automated process which allows for the discovery of unknown substances in an analysis. The acquired data is submitted to the discovery toolset, where it will firstly propose an elemental composition before sending the information out to external libraries in search of plausible substances. Mole files are then returned of probable candidates and then brought into the software, where it will automatically generate in silico fragmentation, which is then compared to the acquired high energy MSE data. So the next few slides will discuss the newest addition to the Waters high resolution portfolio, the Xevo multi-reflective time of flight mass spectrometer, or also known as the Xevo MRT. One thing to note is the methods that we've got currently on the Xevo G3 QTOF, we have directly implemented on the Xevo MRT together with the toxicology library. This is the next generation benchtop QTOF, bringing together the high sensitivity of our robust Xevo TQ Absolute system in combination with the innovative multi-reflective time of flight technology that was pioneered in the Select Series MRT that we launched back in 2021 ASMS. The Xevo MRT, with its incredible performance in a very compact footprint, has been designed to address the challenges that many other scientists have told us about. The challenge to basically further the comprehensive analysis of complex matrices and the need to scale throughput for efficiency and productivity. Basically, scientists want to process more samples in less time. So what I am going to show you in the next couple of slides is some preliminary data that was performed in the Xevo MRT for this project and for this presentation. And what we've done is injected 3 different types of samples: a system suitability injection, a mixture containing labile compounds, and also some authentic urine samples. As mentioned previously, the toxicology screening solution that is currently on the Xevo G3 QTOF was implemented together with the toxicology screening library. So the samples in a little more detail. The system test is our Waters toxicology system suitability mixture, which contains 10 compounds eluting over the 15-minute chromatographic gradient. This was injected at a concentration of 25 nanograms per ml. The 10 compounds are listed just below there. The labile compound mixture contained amphetamine, methamphetamine, and MDA. These were spiked at 3 different concentrations: 10, 100, and 1000 nanograms per ml. Fentanyl and temazepam were also added to this mixture as representative non-labile compounds. This is to ensure and try and test out to see if in-source fragmentation was present or not. And finally, the authentic samples. We injected 10 urine samples, which were diluted 1 in 10 with mobile phase A or 5 millimolar ammonium formate. So just to summarize that analyses, everything either spiked or diluted was with mobile phase A. The solution, the forensic solution, was implemented on the Xevo MRT, which included a 15-minute gradient in positive ionization mode using MSE, and a 5 microliter injection was made. So shown here is an example of the system suitability injection at 25 nanograms per ml. And this was processed using a plus or minus 5 parts per million precursor mass tolerance and a 2 millidalton fragment ion mass tolerance. All 10 compounds which were expected have been identified within the retention time tolerance of plus or minus 0.35 minutes. And as you can see, all with excellent mass accuracies, all less than 1 part part per million. Here we have a scatter plot for the system suitability test mix with a RMS error of 466 parts per billion for 15 replicate injections. Here is another example. This is this time of the label compound mix that was analyzed. For demonstration purposes, I have highlighted methamphetamine, showcasing the excellent mass accuracy, but also illustrating that there was little to no in-source fragmentation found for the low energy spectral data trace. And here is an example of the 10 authentic, one of the examples of the 10 urine samples that was injected, 1 in 10 dilution. As you can see, there are a number of identifications, again, all with excellent mass accuracies for the precursor and fragment ions, and in this case, for the case of methadone. This slide displays the overall precursor and fragment ion mass accuracies obtained for the 10 authentic urine samples. On the left here, we have the frequency distribution plot for the precursor mass error for the 160 identified substances with a mass range of 120 to 500 AMU, identified in the 10 anonymized samples with an RMS error of 571 parts per billion and achieving a 94% detection rate within 1 part per million mass accuracy. On the right, we have 2 frequency distribution plots for 92 fragment ions with a mass range of 80 to 300 obtained for 23 randomly selected substances that were identified of the 160 detections, which achieved 96% detection within 1 ppm. And what we wanted to show and what we managed to show is the power of mass accuracy. Here we have an example demonstrating exactly that and how an incorrect identification was avoided. The substance identified here was anabasine. It is an alkaloid found in tree tobacco and is a structural isomer of nicotine. The detection results look good based on the positive identification criteria I've mentioned previously. However, looking at the high energy information, it shows a slightly different story. If we look at the mass error of the top 3 fragments, all of them are less than 0.2 millidaltons. However, the 4th fragment, one that I've highlighted in that bottom box there, has a mass error of 1.5 millidaltons. Knowing this information, I had a quick look at the alternative assignment to understand why anabasine was the better match compared to the nicotine. The precursor mass and the number of fragments were all the same. It was only the only difference was the retention time error, which favored the anabasine. The best match was based on the retention time tolerance of plus or minus 0.35, the mass accuracy tolerance of plus or minus 5 ppm for the precursor and 2 millidalton for the fragment ions. However, as mentioned in the previous slide, the 4th fragment with a mass of 131 for anabasine had a mass error of 1.5 millidaltons, potentially alluding to the fact that this could be a false positive identification. So, as you know, the Ziva MRT is built for its resolving power and speed, and we wanted to utilize this and ensure we get the correct identifications. And so the positive identification criteria was modified as shown here. The section highlighted in red denotes the mass accuracy tolerance that was used, which favored the anabasine match. The section highlighted in green shows the modified mass error tolerance that was modified mass accuracy tolerance by reducing the precursor and fragment ion mass tolerances to 2 ppm for the precursor and 0.2 millidaltons for the fragment ions. This meant that the fragment ion number 4 for the anabasine was then removed, meaning that the expected number of fragments for anabasine became 3 out of 4, which then brought the nicotine identification as the main best match for the peak itself. As you can see, the precursor mass is less than 2 ppm, but more importantly, the fragment ions have all mass errors of less than 0.2 millidaltons. So in conclusion, the Waters high resolution portfolio, which includes the Xevo G3 QTOF and the Xevo MRT, have shown to be a perfect fit for toxicology screening laboratories owing to its high specificity and excellent mass accuracy. When coupled with the comprehensive Waters toxicology library, the MSE mode of acquisition provides a high confidence in identification during targeted analysis, achieving excellent mass accuracies. Reducing false positive identification is essential in achieving efficiency, resulting in more efficient data review and resulting in a number of samples being reduced for confirmation analysis and reducing the unnecessary expenditure, leading to positive impact on the environmental sustainability. New compounds or MPS type compounds need to be identified, can be identified from derived elemental formulae and online database searches during discovery type of analyses. Waters' dedicated forensic toxicology application team and field teams have many years of experience supporting high-resolution screenings. So whether you choose the workhorse, that is the Xevo G3 QTOF, or opt for the high performance of the Xevo MRT, we will be able to help you with any of your applications. So I'd like to take this opportunity to thank Dr. Michelle Wood and Dr. Mike McCullough for their guidance. And I finally like to thank you for your attention, and I'd like to open the forum up for any questions.
Thank you, Nayan, for that great presentation. And here we do have our contact information. So we have my contact information as well as Nayan's. While we are waiting for a few questions to come in, please use that chat box, or excuse me, the Q&A box to submit any questions that you may have. This is also a good time if you'd like to fill out that survey. Additionally, we do provide a certificate of attendance for those that need this for continuing education credits. So if you do need a certificate, please email me directly and I will be sure to get you one of those. So Nayan, that was a really great overview of the solutions that we have for the MRT and toxicology. So really exciting. And we do have a few questions here, so I wanted to kind of get started on that. And I think one of the ones that I've, find, and you may have touched on it a little bit, but I think is important, is, how easy is it to add a new compound to the library? Or what if you wanted to create your own library? How would someone go about that? And what would you do for that?
Yeah, so creating library entries are pretty simple. It's just a matter of injecting the compound using the gradient, the toxicology gradient that we have, and then letting it process. Obviously, you'd know what compound you'd be injecting. So, for example, you want to add cocaine to the library. So what you'd initially first do would be to search for a mole file or chemical structure from ChemSpider, say, and download that mole file onto your laptop or computer and put that into the library, create a library entry just for the mole file itself. Once you've done that, then you'd actually inject the cocaine standard. This will enable you to get the retention time, but also help to process the data base and help you to get the fragment ion information as well, using the in silico fragmentation based on the chemical structure. And then you can right click and send that to the desired library.
Okay. How long do you think that process typically would take, in theory, just to give a ballpark idea?
So that could take up to about say 17 or 18 minutes, and this is inclusive of the running time as well. So 15
Oh,
minutes
okay,
of
of the method.
running, and then the
Yep.
2 minutes effectively just reviewing the data, making sure you got the fragments it's matched to, looking pretty obvious, and then it's just a matter of right clicking, putting it into the library. Putting it into the library, it takes less than 10 seconds.
Okay, great. I think that's important to utilize. But then once you have the library, it's there, and then it can be used for all the screening and moving forward. So
Absolutely.
initially, right? Okay, great.
The good thing is that you can actually screen. You can do your screening analysis based on in silico fragmentation. So you don't really need to run. You don't need reference material to create a library. You can create a library based on in silico fragmentation and just mole files. Obviously,
Okay.
the more information you have, the better. So retention time and fragment ion information. But if you don't have that information, if you don't have the reference material to do that, to get that information, then the next best thing is just to get the mole files from, say, ChemSpider, and then create your own in silico fragmentation library, and you can screen against that.
Okay. Well, and that kind of ties into a question about how reliable is the identification without the use of reference materials.
Reference materials, I mean, when you do find an identification, especially based on in silico fragmentation or the mole file, a reference material would need to be used for confirmation, just to make sure that what you're seeing, what you saw is what it actually is. So reference material is essential for confirmation of that
Okay.
identification.
Gotcha. Um, and we have another question here. So it says, this is from Stephen, the urine diluent chute looks good. Do you have any data on samples such as postmortem blood where the main issue is extraction? If we don't extract, we'll never see.
Unfortunately, Stephen, we don't have access to any post-mortem bloods, but I'd be
At
happy
this
to
time.
receive any at the moment.
Yeah.
But it'd be great to get to hold of some post-mortem blood and test it out.
Yeah, and we're also looking, working with collaborators as well to be able to assist with that and being able to provide that as a method and extraction capability on these systems. So we are working towards that. It's still a work in progress, I think is the best way to describe that. And Stephen's going to reach out to you, Nine. So we're
Perfect.
good.
Thanks, Stephen. Yep.
So, so we have a question from Yasna here. That's what is the LOD for THC and amphetamine on the MRT? I don't know if we have exact numbers on this, but we might have like ballpark ideas,
Yes.
maybe.
So I don't know about the THC, and I don't know exactly the LOD for the amphetamine, because that was injected in solvent at 10 nanograms per ml, and I was able to see that very clearly. The real test would be when it's actually in matrix, which I haven't done yet. So I'm unable to answer that question yet.
But that's foreshadowing, because we will be doing an additional set of information, providing some for the current trends in forensic toxicology in May, as well as later tox shows this year that are going to continue to build upon this data. So please check back for more information in our site as we build on these methods. There's a few questions here about the library itself. So is the chromatogram directly uploaded into the library for analysis? And how exactly would you use the library? So would you be able to just go into some brief like overview, Nyan, just kind of if someone does an injection, like how it works to compare your your unknown sample versus the library, just to kind of walk through that portion briefly.
Right. So when you are creating the library, you are not putting any chromatograms or any spectral data into the library. it's purely based on accurate or exact masses. So the exact mass is based on the formula for the precursor, and the exact masses of the fragments as well, based on the formula itself. So if you are effectively cherry picking these ions out of the masses of ions that you get. Remember, this is full scan data, so you're going to get all of the masses all of the time. So what the software is doing is you've got a mass of, for amphetamine, 136.1234, and it's looking for that mass within a tolerance that you've set, and that's what it's doing. That's how the matching goes about. So it effectively looks in the low energy data first to see if the if that particular compound is present. If it has found the that compound amphetamine, then it will take that information, put it into the second bucket, and then when it's done that first lot of the first pass of processing the data, it'll look at the second bucket and then start to delve a little bit deeper into the extra information. So then it will start looking at the high energy data, and then we'll actually see if the fragments for amphetamine 119 and the 91 ion, are they present in the high energy data? If they are, and then also look at the retention time, then it'll say, right, I have a positive identification for amphetamine, we're going to be reporting this. And then it comes down to the filtering, the review tab, effectively. In the review tab, you can check, you can have a number of workflow steps, and these are just filters that you've designed to show only what you want to see, effectively. So if you want to see a true positive, so the criteria for my true positive would be within 5 ppm, and this is for the G3 QTOF I'm talking about, within plus or minus 5 ppm, minimum response of 10,000 counts, and at least one diagnostic fragment. If an identification of a peak satisfies all 3 of those criteria, it will be in my most confident workflow step, which basically means I don't really need to spend too much time reviewing that data. So we're getting the software to do all the work for you. If you just set up the filters up front. I mean, we do have within the media, we do have a number of filters already set up. So it's just a matter of implementing that, and then you can modify that according to how you want to see and review your data.
Awesome. That's good. I think that's really informative to be able to provide that information. Thank you for that.
Sorry, that was long-winded.
No, it was great. I think it's important to understand that, because sometimes people may not be aware of the simplicity that can be done once it's set up, right? And it's kind of, you let the software do it. So we have another question here. Have we evaluated the effect of the ESI voltage on adduct formation with the library or on the HRMS, on any of the systems?
So voltages, so you mean how it affects the
probably probe voltage, and how it, like, if you see like sodium adducts versus
yeah.
I mean,
so
you want to look at proton, but
I have not seen any sodium addicts or any salt addicts. I'm just going to generalize any salt addicts in my analyses. I look for them, but I've not seen any. I think it comes down to the cleanliness of the system and the mobile phases, effectively.
Okay. Sounds good. And that goes back to, making sure you're doing proper sample prep at the front end, especially if you potentially have a more complex matrix that you're working with. Great. All right, we have another question here from Carlos. So, hi, thanks for an interesting presentation. Which are the innovations of the Xevo G3 compared to the G2 version? I used to work with the latter. Do you still need to calibrate the mass spec every day and use an infusion reference for mass calibration / alignment? No.
So you don't have to calibrate every day. The calibration is very stable for the G3 QTOF. So let's start again. So when you first get the instrument, you would need to calibrate the system just to kind of effectively stabilize the detector. once the detector is actually stable, it's very stable for a month. And I tend to calibrate it once a month if I'm doing any analysis, but I don't really calibrate that often. As long as the lab environment is stable and there's no temperature fluctuations, so 10 degrees difference between the morning and afternoon, then there's not going to be a problem with the calibration at all.
Gotcha. Okay. Thank you. And when we're comparing to like the G3, because you're talking about some differences, and then the new MRT, how does the sensitivity compare between the two so far in the research and the work that you've done?
So the sensitivity between the two is comparable. One thing to note is the detectors are different, so we can't compare the two detectors, the two systems, because the sensitivities, they're comparable. That's all I can say at the moment, from what I've seen in my hands. Yeah, I don't really know what else to say. I'm not.
No.
I'm not,
I think that's fine, and I think as we build out, and I think that's important to also notice is that the MRT is built on the front end technology of the MRT is built in on the Xevo TQ Absolute.
TQ,
So
yeah.
Yeah, Absolute, right? Yeah.
Yes.
And so we have that front end capability on there, and continuing to build out the toxicology applications for it.
Yeah.
And so
the main thing that you need to understand is the purpose of the Xevo MRT is the speed and accuracy as opposed to the sensitivity. We are looking for absolute resolution of the system, and we are able to get up to 100,000 resolution on that on the Xevo MRT compared to what we would do on the Xevo G3 QTOF.
Okay. And so another question that's come in is, so we've talked, like you talked about the targeted analysis, semi-quant, and then non-targeted analysis for the G3. I know there's a lot of discussions back and forth between whether or not high resolution instrumentation can be used for like quantitation, or you do quant on a single instrument as HRMS. Can you touch base based off of your experience so far? Would this still be seen more of as a semi-quant based instrumentation for the MRT, or more just like qualitative screening?
I think this we're going to be getting more and more iterations of the software that will kind of hopefully push it towards a semi-quantitative type of instrument where we can actually do qual type of analyses, but that's going to be slightly later down the line. Hopefully not too late.
Yeah. Well, yeah, and this is still evolving, right?
Yes,
like it was released in June of 2024, and
yeah.
we're, adapting this to the toxicology screening platform and portfolio. So we're still working towards everything, and you're learning as we go. So I think that this is a good start as we continue through. So. Gonna give another minute or so to see if there's any other questions that may pop in. I do want to say that, I really appreciate all the questions that we do have that have been asked by the audience today. And, as I said, we are continuing to build upon this. There will be more data forthcoming. We will be having additional applications presenting this at local shows. And so we are also going to make sure that everything, there are additional webinars also coming down the pipeline on drugs of abuse and hair, and potentially some other ones. So please be on the lookout for that. So just kind of want to put a plug in there again. Last thing too, the certificate of participation email, you can email myself, which is listed here on the slides, which is Rachel _Lieberman, which is my last name, @waters.com. So that should be where you can provide that particular email to or information to, and then I can get that to you. And I do not see any other questions coming in. Nyan, do you have any last words or anything that you would like to say before we?
No, just look out for more and more of our presentations and updates from myself or my work colleagues for the toxicology solutions that we have. Really,
Okay.
hope to see you soon.
Yeah, definitely. And again, please fill out that survey too if you get a chance. We do appreciate it. And hopefully this was really informative for everybody. We really are excited about getting this information out to you guys and providing what we can. And we really appreciate your attention. So we want to thank you again. Look out for more webinars and lots of stuff. And we hope you have a great rest of your day. Thank you very much.
Thank you.